Dear student, now this is a video lecture that is given by me, Amitava Bhaduri, Assistant Professor in Physics, Barakpur Rashtraguru Surnath College. And the topic of discussions for today's lecture, as you are seeing here, transistor biasing and stability. Students, you know that transistor is a very important semiconductor device, like diodes and some other semiconductor device. And this transistor has manifold applications. There are various applications for the transistors. Different circuits are there. But one of the most important applications and the use of the transistor is its use as an amplifier. And you perhaps know that amplifier is a circuit which can amplify a signals. So transistor can also used as an amplifier, and that is the main use of the transistor, apart from its various uses. Now, when we are going to use transistor as an amplifier, some of the important parameters are to be maintained so that these amplifiers can work efficiently. If any of these parameters is malfunctioning or any defects occurs, any limitation comes associated with the circuits, then that will actually destroy the sole purpose of the amplification process. So, in today's discussions, we will concentrate ourselves to discuss the different aspects of the transistor circuits, specifically how to bias a transistor circuits, and once the transistor circuit is biased, whenever it is acting as an amplifier, how the biasing stabilities can be achieved. Biasing stability, that is also a very important factor, and we shall discuss all these things subsequently, point to point. But the motto of the today's discussion is to make you aware that how a transistor can be used as an amplifier, and at the same time, once we use a transistor as an amplifier, how we can efficiently bias a transistor circuits, and at the same time, we have to see whether the biasing is stable or not. If it is not stable, then that will destroy the very purpose of the amplifications. So, let us begin. This is the lecture's outlines. These are the few points that we are going to discuss today. Objectives, then we have an introductions about this transistor biasing and its stability. Then we have another very important point of discussions, and that is about the DC operating points. What is DC operating point? That we will definitely going to discuss, because that is very much linked with all these biasing and stabilizations. Then we have different kind of biasing circuits to be discussed. Various biasing circuits are there. Starting with, you see, base bias circuits, emitter bias circuits, then so you have a collector feedback bias circuits, and lastly, and the most importantly, is the voltage divider bias circuit. We consider here 4 biasing circuits. The role of this biasing circuit, the purpose of the biasing circuit will be discussed point to point in the various slides that we are going to prepare for these presentations. But above all, we are going to discuss the 4 basic biasing circuits. Then few points of the troubleshooting, that if any type of limitation comes, what are the cause of this limitation, and what are the remedies of the limitations. That's we are going to discuss, and at last the summary. Regarding the objective of the today's discussions, we have some points that we are going to discuss elaborately. The first is that discuss the concept of DC biasing of a transistor for linear operations. Now, what is linear operations? Linear operations is a special type of operations applicable for the transistor amplifier, where we are expecting that the output signals is a faithful representations of the input signal. That means if the input signal is the sine curve, the output signal should also be either sine curve or the cos curve. There should not be any deformations. So whenever the transistors acts in these particular fashions, then we can summarize its total applications as linear operations. Then we have analyzed the voltage divider bias. As I already mentioned, that we are going to discuss the 4 different bias circuits, and out of these 4 bias circuit, voltage divider bias circuit is one of the most important and the versatile bias circuit, having a lot of advantages. It may have some demerits, but at the same time it has a lot of advantages. So that is why out of these 4, voltage divider bias circuit is one of the most important bias circuit that we have to consider. Apart from that, we have base bias, and then we have collector feedback bias circuit. We have to analyze them. Although this analysis of this bias circuits involves several mathematical steps, but we are not going to discuss all the mathematical steps for the analysis. We have taken few points, and we actually try to focus our full attention to understand the physics behind this. Mathematical steps you can find in any of the standard textbooks. So we are not going to tackle all the mathematical steps, but few important points definitely is going to be highlighted. Then basics troubleshooting for transistor bias circuits. You know, the troubleshooting is something which we cannot ignore whenever we are using any type of devices. Similarly, whenever she was going to make a bias circuits or going to make a transistor biasing circuit, then sometime these circuits may render certain kind of malfunctioning. Various causes are there. But the true fact is that circuits may sometimes malfunctions. That means it can function in such a way that you are not expecting. Whenever something is going beyond of your control, so that is nothing but malfunctioning. So definitely in this case, there is a chance of certain kind of malfunctionings, and this malfunctioning is considered to be the troubleshooting. So you have to find out what are the causes behind these basic troubleshootings, and what are the remedies, what are the precautions that are to be taken in order to minimize this type of troubleshootings. Regarding introductions, the terms biasing is used for application of DC voltage to establish a fixed levels of current and voltages. Basically, dear students, you must know that in a transistor amplifier or even an oscillators, for example, transistor amplifier, we have 2 type of voltages. One voltage is called the DC voltage, and another voltage, of course, is the AC voltage or the AC signals. These 2 voltages, they have their respective roles. DC voltage is meant to provide the biasing of the transistor circuit. What is the simplest meaning of biasing? Biasing means in order to run a transistor, you have to give appropriate current and voltages to its base, to its emitters, and to its collector, or base emitter junctions or the collector base junctions. You have to give certain proper values of the voltage and current which are definitely DC. So provision of these DC voltages and currents to a transistor circuits, that is basically the purpose of biasing. So the term biasing is used for application of DC voltages, not AC voltages. Remember this very crucial point, that the moment you are going to discuss anything about the biasing of any transistor circuit, you first of all focus your entire attention that you are going to apply the DC voltage, not any AC voltage. AC voltage is applicable to a transistor amplifier in order to amplify its input signal so that you can get a strong output signal. But as far as the biasing of circuit is concerned, you have to apply the DC voltages. So this is a very important point. Transistor must be properly biased with the DC voltages to operate as a linear amplifier. What is this linear amplifier? I just mentioned, but I can show you what is the purpose of the linear amplifier in few of the diagrams. If amplifier is not biased with correct voltages on input and output, it can go into saturations or it can go into cutoff regions. What is this saturation regions and the cutoff regions? As a student of electronics, if you studied electronics even in the class 12, so you can see that the transistor's characteristics can be divided into three broad regions. Saturation regions, one, second is the active regions, and the third, that is the cutoff regions. Basically, saturation regions and the cutoff regions are the two regions which are prohibited for you whenever you are using a transistor as an amplifier. Mind that, this is a very important point to note. Let me repeat it again. Three basic regions are there in the characteristics curves of a transistor outputs: saturation regions, active regions, and the cutoff regions. Out of these three, you have to deal with the active regions, because that is the only region which is useful whenever we are using a transistor as an amplifier. But when you are using the transistor as a switch, then you can use the saturation regions or the cutoff region. But as far as the transistor is being used only for the purpose of amplifications, definitely active regions should consider to be the most important part. So if the amplifier is not biased with correct voltages or input and output, it can go into the saturation regions, it can go to the cutoff region, which is not at all desirable, because that will cause a certain kind of disaster. I will show you that if anyhow the operation of the transistor go into the saturation, what will happen? And at the same time, operation of the transistor go to the cutoff, then what will happen? But I must say that these two effort is not at all desirable for us. There are several methods to establish the DC operating point. What is operating point? That also will come into the picture subsequently. Go for the next slides. Our subject, this I think these portions, okay, I think it is repeated. Discuss the concept of DC biasing of a transistor for linear operations. So that is the most important objectives behind the today's discussions. Analyze the voltage divider bias circuits, analyze of the base bias circuits and the collector feedback bias circuits. That is the second objective. And the third one is the basic troubleshootings for the transistor bias circuits. I think these slides by mistake repetitive in nature. Okay. Now come to these important slides. Here the title is Amplification of Electrical Signals. Dear student, this is the main scheme which help you to understand what is basically the terms amplification means. Look at here. This is basically a transistor amplifier circuit. These bluish rectangles suppose your transistor amplifier circuits. It has two inputs and it has two outputs. It has input voltage V ins, it has output voltage V outs. Input current I in, output current I out. So these four are the important specifications for any of the transistor amplifier circuits. Now, transistor amplifier circuit always worked with the help of AC signal. You have, this is your input AC signal. This one is its amplitudes. So this one considered to be your input signal. That means you are giving this signal to the transistor amplifier circuits. But in returns, you are getting a signal like this. If we compare the size of this signal with these signals, you can find here the amplitude is greater than the amplitude of this signal. Amplitude of this signal is slightly greater than the amplitude of these signals. So if the amplitude is greater of the output than the input signal, that means amplification has been achieved. And in order to have a kind of qualitative aspect of how the amplification has been achieved, you have a very important parameter, that is gain. And gain means output voltage by input voltage. As long as output voltage is greater than input voltage, your gain is greater than 1 and your amplification has been done and the transistor is working as an amplifier. Now, one point I would like to mention in this regard, that look at the shape of the input signal and output signal. This is the shape of the input signal and this is the shape of the output signal. You find that the shape of the output signal is almost identical with the input signal. Whenever your amplifier works in this fashion, that is the most desirable patterns of working of an amplifier. This is called faithful representations of the output in comparison to the input. You have full input signal, you have full output signal. Only positive peak will be replaced by the negative peaks because there is a phase change of 180 degree in between the input and the output of an amplifier whenever it is used in the common emitter mode. But the shape of these and the shape of these, they are almost identical. Full cycles of the inputs you can get as the output. So this is the most desirable sort of operation for any amplifier. If anyhow the output signal does not look similar to the input signal, some portion of the output signal, suppose that is cut here, so that is called the distortions. That is called the distortion, which is undesirable for us. So this biasing is very much linked with these distortions. This is undesirable, so definitely we have to very much cautious about the methodology through which the biasings can be done so that this type of distortions can be avoidable. Distortion is not at all desirable for us. We always need this kind of output voltage, which is the faithful representations of this input voltage. Now look at here, few points that is written during the working of a transistor's amplifier. So we have to apply the small amplitude AC signal that I have shown you in the previous slides to the input of the amplifier, and this AC signal added with the DC biasing voltage. These signals that I had shown to you in my last slide, this AC signal was simply added with the DC signal. The DC signal comes due to the biasing, and AC signal is the signal that you have given to its input. So what is actually happening? This input signal is simply added with the DC biasing voltage. So with the effect of that, the base current will try to swing, that is try to change periodically. I am showing you a slides in order to look at here. Look at here. Look at here. See, this is the swing of the base current, because this is IB. IB is meant for the base current. IB is meant for the base current. So the base current of the transistors may swing, have a swings like that, and the swing of the base current is giving rise to the swing in the collector current. So the base current varies periodically, and these periodic variations of the base current eventually created a periodic variations in the collector current. IC stands for the collector current. Okay, I will come back to this once, but before that, let me discuss few points and then I will come back to it. So, therefore, we see that the AC signal, wherever mixed with the DC voltage, that is eventually going to vary the base current periodically, and by the collector current is also going to be vary. Due to these variations of this collector current and the base current, one very important point regarding this transistor biasing, that is called the Q point. This variation of the collector current resulted a continuous shift in the Q point of the transistor circuits. Q point sometimes goes up, sometimes goes down, and that I shall discuss. But this Q point will shift over a load lines. Q point will shift over a load line, and due to the shift of the Q point, if anyhow the Q point enters to the saturation regions or even in the cutoff region, that will bring disaster for transistors operations. If anyhow the Q point goes to the saturation regions or even in the cutoff region, so that will actually bring certain disaster, that will bring some distortions. I will show you everything in subsequent slides. So for a faithful representations of the output signal, which we actually need with respect to the input signal, it is very much required to have an arrangements in the circuit which may ensure the fact that Q point should lie in the active region of the characteristic curve. Q point should lie in the active region of the characteristic curve and be stable. So first of all, there are two things that has to be maintained. One is the Q point should be selected in such a way that its position should be at the within the active regions. It cannot go to the cutoff regions, it cannot go to the saturation region. So first is the selection of the Q point, and the second is, once the Q point has been selected, then the second factor is the stabilization of the Q point. You can select the Q point, but the Q point should not go to the cutoff regions or the saturation regions. It can move, but it cannot go to the cutoff or the saturation region. So a stability is also needed, and the stability is also needed. Now, here there are three important points, but before I am going to discuss all these things, I must say the Q point is a very important point regarding the biasing, and the Q points you can find here. Look at here. This one is a transistor circuit. This is an NPN transistors we have taken. This is the base. It is connected with an RB base resistance. This is an variable voltage source, and the collector is connected with an collector resistance 220 ohm, and that is connected with the variable voltage source. Okay. So in this case, the collector current depends on the collector to emitter voltage, and how it depends, we have in graphs like this. These are called output characteristics curves, IC versus VCE curves. In these curves, you can find these regions. This is called saturation regions. This is a region. This one is called the cutoff regions. So this one is the saturation region. This one is the cutoff regions. This is dangerous. This is dangerous for you. But between this to this entire region, that is called the active regions. But what is Q point? Look at. You were seeing a straight lines. You were seeing a straight lines. This is a straight line. This straight line, that is called the load line. This one is called the load lines. And these are the different characteristic curves. And all these characteristic curves are associated with a certain values of the base current. For example, if we take this one, the base current is 200 microampere. Here 400 microampere. So this is the load lines, and these are the different characteristic curve. These are output characteristics curve. And these are the intersecting points between the load lines and the characteristic curves. And these intersecting points are known as the Q point. Remember, Q3, Q2, Q1, these are all Q points. They are called the quotient points. And these quotient points are very important for the working of a transistor as an amplifier. So these are called the Q points. You may not have a Q points here. Dangerous. Q points, if enter to the saturation regions, will bring distortions. At the same time, the Q points, when comes at the cutoff region, it will again brings a disaster for you. That means the output signals will not be faithful representations of the input signal. So what we are expecting? We are expecting that our Q point should lie in the active regions. Our Q point should lie in the active regions. And most appropriately, Q point selection should be such that its position of the Q point is here. This is the most, you can say, the stable and most important selections of Q point if it is staying here. So we are going to fabricate the transistor's amplifier circuit in order to ascertain a fact that my Q point, DC operating point of the Q point should be here. It may be here or may be here, but it should be at the middle of the active region. So that is the most desirable things. Now, the choice of these Q points at the middle of the active region is the selection of DC operating point that is to be mentioned in that slides. So again, so these Q points is very much depends on the collector current, the collector current which is passing through the collector. If anyhow your collector current change, your Q point should also change, but Q point should lie on the load line. It can move in the upward direction or it may move in the downward direction. Why? Because of the change in IC. IC depends on these three important factors: ICO, beta, and VB. ICO is a kind of reverse saturation current passing through the collector base junctions, and this is highly temperature dependent. In fact, for 10-degree rise in temperature, ICO becomes just double. So you can realize how this IC depends on temperature variation. Beta, which is equal to IC by IB, it is called the internal current gains of transistors in common mode configuration. That is also very much temperature dependent. VBE, base emitter voltage, that is also depends on temperature. So all these three parameters for any transistor, they are depends on temperature. So even there is a fluctuation of temperature, these parameters are going to change. The thing is that if any of these three parameters is going to change, that will eventually going to change the collector current. That's going to change the collector current. And if your collector current change, that will automatically change the position of the Q point. So that is the problem. You have chosen the Q points, but if any three of these factors is going to change, these Q points may drift over the load lines. It can go to the saturation regions or even it can go to the cutoff regions, but that is not desirable. So that is why attempt has been made in order to devise the circuit in such a way that we can minimize the effect of the variation of ICO, beta or VB on IC. That means their effect, their variation can be, their variation of IC with ICO can be minimized. Attempt has been made. Similarly, the variation of IC with beta can be minimized. So you have to devise the circuit in such a way that the effect of all these three factors, they are definitely going to change because of the temperature fluctuations. You don't have any controls over the temperature fluctuation. It will definitely come. But your IC should not be abruptly changed to a very large magnitudes, because that can put the entire thing in a very difficult situation. Your Q points may enter to the saturation regions or even in the cutoff region, and that will bring the distortion. So therefore, the question of stabilizations come. Meaning of stabilizations in a very simple language is that we have to devise the circuit in such a way that the effect of this variation on capital IC, a collector current, may be minimized in order to safeguard the stabilizations of the Q point. Now, this particular effect, the stabilizations, can be measured by an important parameter, and that is given by here, S. This is called stabilizations coefficient. This is equal to delta IC by delta ICO. That means partial derivative of IC with respect to partial ICO, keeping beta and VBA constant. So this one is called the stability factor. So for any circuit, we have to calculate what is the stability factor, and this can be calculated mathematically with a very small algebraical steps. Anybody can calculate the value of capital S. So you can calculate the stability factor. Why you are calculating stability factor? Because that is an qualitative aspects for the stabilizations of Q points. What is better? Lowest value of S is better. If S is very large for any circuit, that circuit is totally, you can say, is totally useless circuits, because the operating points in that type of circuit will fluctuate to a very large wide range. It may go to the saturation, it may go to the cutoff regions. So therefore, our purpose of the stabilization means we have to devise the different electronic circuit that we are going to discuss today in order to minimize the value of S, and the most appropriate value of S is 1. If you were able to get S equal to 1, that is the most efficient, you can say, the stabilizations of the Q points. For the transistor biasing, we basically need these three important factors. Biasing. Emitter based junction is to be forward biased, collector based junction to be reverse biased, and proper zero signals collector current. That means zero signal collector current means whenever you are not attaching any input signals to the base, even though some DC current should flow through the collector. And this DC current comes due to the DC biasing voltage. So this is called zero signal current. So the proper flow of zero signal collector current and the maintenance of proper collector emitter voltage during the passage of signal is called transistor biasing. So this is the definition. That means the moment you connect few DC voltages in order to establish an DC collector current and DC collector to emitter voltage, for that there is no need from your side to connect an AC voltage. There is no need. You are not connecting any AC voltage, but even though there is some DC current flowing through collector, so that is the zero signal collector current. And there is a potential difference between the collector and emitter. That is called collector emitter voltage, and that is also zero signal collector emitter voltage. So the setting up of zero signal collector current and zero signal collector emitter voltage, that is called the transistor biasing. If the transistor is not biased properly, it would work inefficiently and produces distortion in the output signal that I already elaborated. At the same time, a transistor is biased either with the help of a battery or associating circuits with the transistors. The latter method is more efficient and is frequently used. And the circuit used for transistor biasing is called the biasing circuits. That we will see a separate battery are used for biasing the circuits, when the circuit will come, we'll try to see what are the different battery which are really employed in order to biasing the circuits. And biasing stability, I already pointed out. The operating point of a transistor amplifier shift mainly with the changes in the temperature, since the transistor parameter beta, ICO and VB, these are all temperature dependent. So if any parameter changes, that will eventually brings a change in the collector current, and that ultimately change the operating point, and so the operating points will change along the load line either towards the saturation regions or even then the cutoff regions. Now this one is the most you can say the simplified you can say the biased circuit. This is the NPN transistor, base of the transistor, this is the emitter, this is the collector, and this is connected with this variable power supply. This is called the base power supply here, base emitter power supply, and this one is the collector, is further connected with a variable voltage 0 to 10 voltage. So this will provide the collector emitter voltage, and the emitter is grounded here. Beta DC means IC by IB, which is called the internal current gains, that is equal to 100 here. Suppose these are some typical value, and these I already explained. This is the Q point, this is also the Q point, this is the another Q point, and the most desirable Q point is this one. So we always try to maintain the Q points at the middle of the active region. So definitely this is the most favorable positions of the Q points. Now here, see, whenever the input signal is mixed up with the DC biasing signals, because the DC biasing signal, you see, in the base, a DC battery is there, this is providing a DC current, IB is the DC current. At the same time, whenever we are using a transistor, we are applying an AC signal to the base. So at the base, AC signal is going to mix up with the DC biasing voltage, and in that case the base current is going to fluctuate in this way. It goes maximum, then come here, then it goes in this way. So this is the fluctuation of the base current. This one is called the fluctuation of the base current. Look at here, this is your Q point. Load lines, middle of the load line, this is the Q point. And if this is the Q point here, then obviously what we see, if I drop a perpendicular, so this is called VCEQ. That is the VCE at the Q point. It is called the quotient value of the collector emitter voltage. And this one is called ICQ, that is quotient collector current. So the selection of Q points depends on three important factors. This one, quotient collector current, quotient collector emitter voltage, and quotient base current. So if you provide these three, that will actually fix up the position of the Q point. And I already mentioned that this should be on the load line. Now when this base current fluctuates in these fashions, obviously these Q points will drift in this direction, then comes here, then comes here. In this way the Q points drift. Q point is going to drift in this way, and when the Q point is going to drift, and that will eventually produces a variation in the collector current and variation in the collector voltage, and this variation of the collector voltage will be your output signal. Remember, this variation of collector voltage will be your output signal for the amplifier. So in the input you are changing the base current, that will brings a change in the collector current, and eventually that will brings a change in the collector voltage. So we see all of them are sinusoidal in nature. Everything is fine, nothing wrong happens here. So that is expected. This is expected. This is called the AC load line. But sometime the things does not proceed in the way that we are expecting. Suppose by any eventuality, the Q point, which was supposed to be at the middle positions, comes down here. So it is going toward this cutoff regions. If it comes down, then what we see? What we see, our output voltage, this portion is okay, but this portion is truncated. It's slightly cut. So I am not getting the full output voltage. I am not getting the full output voltage. Why this happens? Because my Q point, which was supposed to be at the middle, now come here. So now it starts drifting in this way. It's entered to the cutoff region. And as it entered to the cutoff region, that eventually truncated this output signal. So output signal is cut. I'm not getting the full output signal. This portion is full, but this is called the distortions. This one is called distortion, and this is undesirable for us. This is undesirable for us. This distortion is undesirable for us. We are not, anyhow, we have to remove this kind of undesirable thing. Definitely. We always need a full output cycles. Always need. But here it is. Now see, IC, the collector current is also gets clipped. This portion is okay, but this portion is clipped. Any type of clipping brings a kind of distortion effect. Now distortion is undesirable. Now this distortion comes because of the fact that the Q point drifted towards the cutoff regions. In my next slides, opposite things happens. See, in my next slides, opposite things happen. That means now the Q point, which is supposed to be at the middle portions, now comes here towards the saturation region. Whenever it goes to these particular positions, then corresponding you see the output voltage. This portion is okay, but this one is cut, truncated, brings distortion. That means now you can say that this is nothing but a distorted output. That is not at all desirable. That is not at all desirable, because we are not expecting this kind of distorted outputs. But what is the reasons behind this distorted output? Shifting of this Q point from this middle position to this. If the Q point was here, I am getting the full cycles. But Q point has been drifted. Now this drifting of the Q point depends on three factors. One is ICO, second is beta, and third is beta VBE. Because of the fluctuation, there is a drifting of Q point. So what is the need of the hour in order to fix the Q points here? That is called the stabilizations. So we have to use various circuits so that we may fix these Q points near to the active region, so that we can get the output signals, which is the faithful representations of the input signals. The requirement of the biasing networks I already finished up. Ensuring the proper zero signal collector current, VC not falling below of 0.5 volts for germanium transistors and 1 volt for silicon transistor. Now see, this is the factors. This I already mentioned. SICO. This is called the stability factors. Stability factors can be calculated by differentiating IC with respect to ICO, keeping VBE and beta constant. So this is the very important factors you must know. Stability factors for any circuit is given by this formula. And IC, which is the collector current, can be written in these fashions. Look at here. IC is given by this. IC equal to 1 plus beta into ICO plus beta into IB. IB is the base current. So IC is equal to, you can get this from any standard book. So this is taken from the standard book. IC equal to 1 plus beta ICO plus beta into IB. So if I keep that particular equation in mind and simply differentiate, I will get this result. So this is the result particularly useful in order to get the value of the stability factors of a particular biasing circuit. I have to use the 4 biasing circuit So this is the main formula of calculating the stability factors for each and every biasing circuit. And we'll find that which biasing circuit can give us the best value of the stability factors. So let us see what are the different kind of biasing circuits we have. 4 biasing circuit I have already mentioned. This is the first biasing circuit. This is called the fixed bias circuit. Look at here. This is the NPN transistors. Emitter is grounded. Base is connected with the resistance RB, 200 kilo ohm resistance, and that is connected with a DC voltage plus 15 volts. Suppose this is also connected with a DC voltage battery plus 15 volts, and this is RC resistance 1 kilo ohm, and this is the collector. So this circuit looks very simple circuit, but this circuit has a lot of disadvantages, and as a limitation is also there. So let us see why the limitation comes. The circuit looks very simple. You have only a single transistor here, you have 2 resistance, and actually basically this is nothing but a single power source, single source of battery. We are connecting both these terminals, you can short them together and finally connected with the battery. So it looks very simple. Now see the stability factors, you know the definition of the stability factors, SICO, that's equal to this, and this is the final formula for these circuits. Look at here, if I connect them, this I can produce a network here. I can produce a network. If I connect them, so I can produce a network here. So if I apply the Kirchhoff's voltage rules, you know, as a student of physics, every student must know what is Kirchhoff's voltage rule because it was discussed in class 12. Even in your earlier semester, this was discussed. So if I apply the Kirchhoff's voltage rule for this particular network, then you was able to get this one, IBRB. IBRB is the potential drop across the resistance RB plus VBE means this. So this voltage drop plus this voltage drop is equal to VCC. VCC means the voltage that you are connecting with the collector. So VCC is this voltage and this voltage, and if we proceed in this way, then this voltage to this voltage they are same. So this voltage plus VBE, voltage between base and emitter, that should be equal to VCC. So you have this one, IB equal to RB, IBRB plus VBE is equal to VCC. Applying the Kirchhoff's rules, you can get this one. Now you are not getting any IC here, not getting any IC. Simply differentiate this expression with respect to IC. So delta IB by IC, there is no IC here, so definitely IB is totally independent of IC. So delta IB by delta IC should be 0. If we put it 0, A is equal to 1 plus beta, 1 plus beta. The value of beta for the specific transistor that we are using in the laboratory is not about, if it is not in power transistor, it is about 100 or maybe 150 or maybe 200. So if beta is 200 or 100, so S is equal to 101 or 201, that's quite high. So the value of S is high. So this type of circuit for which the value of S is quite high, it's not at all desirable, because if I use this type of circuit, then the operating point once had been fixed can fluctuate so heavily that there's most likely there are enough chance that it can go to the cutoff regions or even the saturation region, and if that happens, that will bring a kind of severe distortions to the output signal. So that is why this type of circuit is not being used, particularly for the amplifiers. Now it has a merit and the disadvantage that I already shown you, that the value of beta is quite large. So 1 plus beta is very large, so stability factor is very large, so therefore that is not very much useful whenever we are going to make any transistor circuit. This one is not very useful. Advantage is very simple, circuit looks very simple, but as far as the simplicity is concerned, that is okay. Simply is the most simple circuit, but is working is not very efficient, because the value of capital S is quite large, which is making the Q point very, very vulnerable. That means Q points drifting is occurs so rapidly that it may enter to the saturation, or it may enter to the cutoff regions, and that will bring some disasters to us. So therefore, it is uses given by, due to the above inherent drawbacks, fixed bias is rarely used in the linear circuits. I already mentioned this point. Linear amplifier circuit, this type of biasing is not being used. Next, come to another biasing circuit. Here, this is called fixed bias with emitter resistors. See, this is also fixed bias because the base and the collector, they are getting supply from the same source, so the fixed bias. But here the only thing is that this emitter is connected with a resistor and then goes to the ground. So this is called emitter resistance. This emitter resistor, previously it was not there. So only things that we included in this circuit is this emitter resistor. Now this emitter resistors can provide a negative feedback to the circuit. A negative feedback, and these negative feedbacks to the circuit can do two important things. One is, because of this negative feedback, the stabilization of the circuit is quite okay. If we compare its stabilization with the previous one, due to this negative feedback provided by this emitter resistor, the stabilization is quite okay for this circuit in comparison to the previous one. But at the same time, the same negative feedback actually reduces the gain. So in this case, although you are getting good stability of the operating point, but at the same time you have to compromise the gain of the amplifiers. Now the gain of the amplifier is another very vital issue. So you can get the good stabilization in this case because of the negative feedback given by the emitter resistor. But at the same time, its gain should be reduced here. So you have to compromise the gain. So that is the things. So that is given, that is written here. The circuit has a tendency to stabilize the operating point. Stabilization is much more greater than the previous one. But the demerit is that the beta value is fixed for a given transistor. This relation can be satisfied either by keeping RE very large or making RB very low. RE means the emitter resistor, the value of the emitter resistors can be made very large, or RB, which is the base resistors, can be made very low. Now, neither of these two is permissible for a very considerable limit. So that is why I am saying you that this particular circuit can give us advantage. That means stabilization is better than the previous one, but at the same time, it is due to the negative feedback which is caused by the RE, the gain of the voltage gain of the amplifiers will be reduced down. So we have to compromise the voltage gain in order to have the better stabilizations. So we have chosen another circuit here. So this circuit is different from the earlier two circuits. Here, the base is directly connected with the collector. Previously, your base was connected with this VCC, that voltage source. But in this case, your base, look at this, base is connected with the collector. It is connected with the collector. So therefore, this is called the collector to base bias circuits. This is the collector to base bias circuit. Here also we can get a better stabilizations. Even the stabilization of this circuit is much more better than the earlier circuits, that is the emitter fixed bias with emitter resistance. It is greater than that. Another advantage is that a problem that make cripples, that is called thermal runaway. Thermal runaway is a problem which is responsible for the burning out of the transistor. If the thermal runaway gets unchecked, that will actually burn the transistor. But this type of circuit may check the thermal runaway. Anyhow, if the collector current increases by any, you can say the causes, the circuit provide a negative feedback, and by doing so, it will try to reduce down the collector current so that thermal runaway can be checked. So, this circuit can provide us the better stabilization. You can connect the stabilization factors by applying the against the Kirchhoff's voltage rule to the circuits, and if we do so, and this is directly coming from Kirchhoff's voltage rule. RF is the one resistance. You see the RF is the resistance. This is your RF. So if you apply the Kirchhoff's voltage rules here, so you get this equation. This you can get from any standard book. You can get this equation from any standard book. So if this is the equation, IB plus IC, RC, IB, RF plus VB, that is equal to VCC. Now you simply take delta IB, delta IC. Delta IB, delta IC, and that is equal to minus RC by RF plus RC. This one. So once you get delta IB by delta IC, from this you can get this one. Now you put the expression of delta IB by delta IC in the expression of SICO, and you will get this result. This one. One thing that is evident, SICO equal to 1 plus beta by something, by something. By something means this is a result which is definitely less than 1 plus beta, because this one is greater than 1, this factor is greater than 1. So obviously SICO is less than 1 plus beta. It is less than 1 plus beta. More the value of this, less will be the value of S. And as the value of S is lesser and lesser in this case, by increasing the value of this one, we are getting better and better performance. So more we are able to increase the value of the denominators, more will be the improvement in the value of stability factor. So here we have a specific choice. We can adjust the value of RC in order to bring the numerators large, and so that I can reduce down the ICO. So that's benefits I am getting, which is less than IB, signifying the better thermal stability. So that benefits I am getting. So these are given here, some merits and the demerits of the circuits. Merit is there, demerit is also there. Beta value is fixed. The demerit is more or less same as that we discussed in the earlier circuits. But the use is that this feedback also decreases the input impedance of the amplifier. Here also there is a kind of feedback. There is a kind of feedback. Feedback means when the output is connected to the input, that is called the feedback mechanism. In this case, a feedback mechanism is also taking place. But that feedback mechanism is, you see, that in addition to the RE causes a feedback which reduces the voltage gain of the amplifier. Here also the feedback is causing a certain kind of voltage gain reductions. The feedback also increases the input impedance of the amplifier when seen from the base, and which can be advantageous. Increase the input impedance. Input impedance is something which is also an important parameter for a transistor amplifier. It will be better that if we have a large input impedance, but in this case this feedback is providing that opportunity. By providing these feedbacks, I can increase the input impedance of this transistor circuits. So these are then comes to the potential divider bias circuit. This is the last circuit that we have to discuss. As I already mentioned, that this one is the most important type of circuit that we have to study. Most important. In almost 75 to 80% of the transistor amplifier circuit, you can find this biasing. These biasing circuits you can find in each of them. It has several advantages. First of all, good stabilization. The good stabilization. Second is that if we replace your transistor by any other new transistors in the circuit, you can get almost the same sort of Q point. So the Q point does not depend on the choice of transistor. If anyhow your transistor burned out, you can replace your transistor by another new transistor. And if you put that new transistor in the circuit, you can find the previous Q point and the new Q point, they are almost like same. So the Q point does not depend on the transistor itself. So that's the big advantage that we are getting from this circuit. I can show you the simplified versions of the circuits look like this. This is called the potential divider circuit. Why it is potential divider? VCC is here. That is a DC voltage. You are connecting a DC voltage. This is one resistor. This is another resistor. So your enter DC voltage comes in between this point and this point. So this R1 and R2 is nothing but a potential divider. Your enter VC has been divided into this section and these sections, and you are taking your input voltage from here. So that is why this is called potential divider bias. So input bias, that means the base bias is taken from the potential dividing. The potential divider circuit is used for the providing the base bias. So that is why it is called potential divider circuit. Then so we have RC, then we have RE as usual. So there are 4 resistances: R1, R2, RC, RE. In order to have an analysis of the circuit, we have to apply the Thevenin's theorems at these particular portions. We have to see this particular portion and apply a Thevenin's theorems to these input networks. If we apply a Thevenin's theorems to the input networks in between the point this and this, then any Thevenin's circuit is equivalent to a Thevenin's voltage and Thevenin resistance. The Thevenin voltage will be given by this VCC R2 by R1 plus R2, and the Thevenin resistance is given by this R1 into R2 by R1 plus R2. So what we are doing here, we are applying Thevenin voltage to the input of the circuits. So if we apply the Thevenin voltage to the input of the circuit, this input of the circuit then reduces to have only a voltage source, that is called the Thevenin voltage, and corresponding Thevenin resistance. So the Thevenin's equivalent circuits will be given by, look at here. Now I apply the Thevenin's theorems for the input of the circuit. Once I do that, the input of the circuit now becomes very simplified. It has a voltage source here, that is the Thevenin voltage. With this Thevenin voltage, we have Thevenin resistance connected in series, and that is finally connected with the base. So the DC biasing now will be given by not a direct battery, but a Thevenin voltage. This is basically providing you the base bias. And then so you have a VCC, that is the a battery connected with the RC. But the base bias should be done by VTH and RTH. And in this case, you can apply Kirchhoff's rules, and in that case this is VCC and this is 0. So enter voltage difference is VCC. So break this voltage difference into 3 important parts. One is this is IC into RC. Second is this VCE. So IC into RC plus VCE plus I into RE, that should be equal to VCC, that is written here. See, that is written here. And if I go here, if I see this particular case, in that case, IB RTH, 1 voltage drop, VBE another voltage drop, and IE RE, this is another voltage drop. So this voltage drop, this voltage drop, and this voltage drop will be equal to VTH. So if you apply the Kirchhoff's voltage rules, by saying any standard book, you can get this result. These results you can obtain there. And once you get this result, take del IC, del IB, del IC from here. Del IC by del IB by del IC from here. So if you just simply partial differentiations, if you partially differentiate this one, then so you will get delta IB by delta IC, and that looks like this one, minus Re by Rth plus Re. And then you put the value of delta Ib and delta Ic in the expression of delta Ico, and then you got this one. So this is the value of the stabilization factors. So at the last, I am just simply using this result here, S ICO, so that is equal to 1 plus beta divided by 1 plus beta, then this can be written as 1 by 1 plus Rth by Re. This. So I can write in this way. I can write in this way. I can write in this factor. So SICO, that is equal to 1 plus beta this one. So that expression can be written in this way. Now suppose if you put RTH by RE, if that is tends to 0, suppose, that means if RE is very large, very large, if you are able to create a situation that RTH by RT is 0, then this becomes 0, means this is 1 plus beta. This is 1 plus beta, means in that case what I get? ICO, that is equal to 1 plus beta in the denominators, and in the numerator also it is 1 by beta. So then that is equal to 1. So S equal to 1 means the highest efficiency. That means you cannot expect an efficiency more than that. That means this circuit has the potentiality to provide you the maximum efficient value of the stability factors, and that is equal to 1. So this circuit can give that benefit which other circuits may not, because so far I already mentioned that S equal to 1 is the highest achievable value of the stability factors. You cannot get better performance than S equal to 1. So this circuit has the potentiality to provide that particular value of S. So that is the reasons why this circuit has been extensively used in various uses. Merits are given there. Operating point is almost independent of the beta variation. If your beta is changing with respect to the temperature, operating point does not change. Operating point stabilization against shift in temperature is also another important advantage. As beta value is fixed for a given transistor, these relations can be satisfied either by keeping Re fairly large. We have to make the value of Re very large. And if I is able to keep the value of Re very large, dear students, the benefit I have shown you in the blackboard, that if anyhow the value of Re is very large, then this factor tends to 0, and if this factor tends to 0, then SICO becomes 1 plus beta, effectively near about 1 plus beta. So 1 plus beta and 1 plus beta, they may simply cancel each other, and eventually you will get S equal to 1. And if you was able to create S equal to 1, you can imagine that what wonderful work that has been done, that your circuits now become perfectly stable. So that is the most important benefits that we are getting for this circuit. And the second benefit is that here the selection of operating point does not depend on the transistor. Even if you change the transistor by another transistor, the DC operating point position will be same. So it can provide extremely good stability, And if you are able to locate the operating point at the middle of the active regions, this circuit provides you the extreme stability. And so this is the most and widely useful circuit for using transistor as an amplifier. So by saying this much, I am going to conclude my today's discussions, and I hope you understood what I mentioned here. Thank you very much.